Angle between two lines using direction cosines. Welcome, everyone. Today, we are going to explore a very efficient way to calculate the angle between two lines in three-dimensional space. Now, if you look back at our previous lessons in three-dimensional geometry, you'll remember that we spent quite a bit of time discussing direction ratios. While direction ratios are incredibly useful, they can sometimes make our calculations a bit bulky. However, today's topic focuses on using direction cosines instead. You will notice that when we work with direction cosines, the mathematical expressions we use to find the angle between two lines become significantly simpler and much more streamlined. The reason for this added simplicity is quite elegant. It's because direction cosines are essentially the components of a unit vector, meaning they already carry a standardized magnitude of 1. This property is what allows us to use the much cleaner formulas we are about to dive into. Understanding direction cosines, DCs. Now that we've introduced the topic, let's take a closer look at what direction cosines actually represent. Think back to our previous discussion on direction ratios. While those are great for describing the orientation of a line, direction cosines give us a more precise, standardized way to look at it. Specifically, the direction cosines of a line are simply the cosines of the three angles that the line makes with the positive x, y, and z axes. To keep our notation clean, we denote these three values as L, M, and N. Now, here is a very important point to remember for your calculations. There is a fundamental property that all direction cosines share. The sum of their squares is always equal to unity, which is just a mathematical way of saying 1. In other words, L squared plus M squared plus N squared equals 1. Keep this property in mind, because as we will see in the next slide, this specific characteristic is exactly what allows us to use that much simpler cosine formula for finding the angle between two lines. The cosine formula for the angle. Now that we have established what direction cosines are, and remember that the sum of their squares equals 1, let's put this into practice by looking at how we actually calculate the angle between two different lines. Suppose we are looking at two lines, which we will call L1 and L2. To find the angle between them, we first need to identify their specific direction cosines. For our first line L1, let's denote its direction cosines as L sub 1, M sub 1, and N sub 1. Similarly, for our second line L2, we will use L sub 2, M sub 2, and N sub 2. The formula to find the acute angle theta between these two lines is quite elegant. Cosine of theta equals the absolute value of L sub 1 times L sub 2 plus M sub 1 times M sub 2 plus N sub 1 times N sub 2. Now, you might be wondering, why do we include that absolute value sign? This is a very important detail. In geometry, when we talk about the angle between two intersecting lines, we are almost always interested in the acute angle. That is, the smaller angle, which stays between 0 and 90 degrees. Because the cosine of any acute angle is always a positive value, we use the absolute value bars to ensure our final calculation remains non-negative. This prevents us from accidentally calculating the obtuse supplement instead. In the next slide, we will see that while this cosine formula is our primary tool, there is actually an alternative way to express this angle using the sine function. The sine formula for the angle. Now, moving on to slide 4. While the cosine formula we just discussed is definitely the more common method you'll encounter, it is important to know that the angle theta can also be expressed using the sine function. You might be wondering where this comes from. Well, it is actually derived from the fundamental trigonometric identity where sine squared theta plus cosine squared theta equals 1. When we apply this identity specifically to our direction cosines, we get this more complex-looking formula. Sine theta equals the square root of the quantity L sub 1, M sub 2 minus L sub 2, M sub 1 squared plus the quantity M sub 1, N sub 2 minus M sub 2, N sub 1 squared plus the quantity N sub 1, L sub 2 minus N sub 2, L sub 1 squared. I know, it looks quite intimidating. However, don't let the complexity scare you. This specific formula is particularly useful when you move into advanced topics like vector calculus, or when you are performing more complex calculations, such as finding the shortest distance between two lines. Step-by-step calculation process. Now that we have explored both the cosine and sine formulas, let's consolidate everything we've learned into a clear, step-by-step procedure. If you follow these 4 steps, you'll be able to solve any problem of this type with confidence. First, you need to identify the direction cosines. Look at your given lines and clearly list out the components for both. For the first line, write down L sub 1, M sub 1, N sub 1, and for the second line, write upon L sub 2, M sub 2, N sub 2. Being organized here prevents errors later on. Second, apply the cosine formula. This is where the actual calculation happens. You will multiply the corresponding components together and then add them all up. Specifically, you'll calculate L sub 1 times L sub 2, then add the product of M sub 1 times M sub 2, and finally add the product of N sub 1 times N sub 2. Third, take the absolute value. As we discussed in the previous slide, we are looking for the acute angle. So, if your sum happens to be negative, simply remove the negative sign to ensure the result is positive. Finally, find the angle. Once you have that single numerical value, you'll use your calculator to find the inverse cosine of that value, which we write as cos inverse of theta, to determine the actual measure of the angle theta. In the next slide, we are going to put this exact process into practice with a real-world engineering example to see how these steps work in a practical scenario. Real-world example, structural engineering. Now that we have covered the theory and the formulas, let's put everything we've learned into practice with a real-world application. Imagine you are working in structural engineering. Suppose you have 2 structural. Stability and safety of that joint, an engineer must precisely calculate the angle between these 2 beams. For this problem, let's say the direction cosines for the first beam are 1/3, 2/3, and 2/3. For the second beam, the direction cosines are 0, 1 over the square root of 2, and 1 over the square root of 2. Let's walk through the solution step by step. In step 1, we simply identify our given values from the scenario. For beam 1, our L1, M1, and N1 are 1/3, 2/3, and 2/3, respectively. For beam 2, our L2, M2, and N2 are 0, 1 over the square root of 2, and 1 over the square root of 2. In step 2, we substitute these values into the cosine formula we discussed in the previous slide. We take the absolute value of the sum of the products, L1 times L2, plus M1 times M2, plus N1 times N2. This gives us the absolute value of the quantity, 1/3 times 0, plus 2/3 times 1 over the square root of 2, plus 2/3 times 1 over the square root of 2. Moving to step 3, we simplify the expression. The first term, 1/3 times 0, becomes 0. That leaves us with 2 over 3 times the square root of 2, plus another 2 over 3 times the square root of 2. Adding these together, we get the absolute value of 4 over 3 times the square root of 2. Finally, in step 4, we rationalize the denominator and solve for theta. To rationalize, we multiply the numerator and the denominator by the square root of 2. This results in 4 times the square root of 2 over 6, which simplifies down to 2 times the square root of 2 over 3. Therefore, our final angle, theta, is equal to the inverse cosine of 2 times the square root of 2 over 3. As we move to the next slide, keep a close eye on how we handled these specific values, because there are a few common pitfalls to avoid when performing these types of calculations. Common mistakes to avoid. First, a very common mistake is confusing direction ratios, or doctors, with direction cosines, or DCs. You might find yourself tempted to use the simplified formula, where cosine theta equals the absolute value of L1, L2, plus M1, M2, plus N1, N2, even when you are given direction ratios like a B and C. Please remember, this simplified version only works if your values are direction cosines, meaning the sum of their squares equals 1. If you are working with direction ratios, you cannot use this shortcut. you must use the more complex formula that includes the square roots in the denominator to account for the magnitude of the vector. Second, do not ignore the absolute value sign. As we discussed earlier in the lesson, when we talk about the angle between two lines, we are looking for the acute angle. If you forget the absolute value, you might end up with a negative cosine value, which would incorrectly lead you to calculate an obtuse angle instead of the acute one we need. Finally, be extremely careful with calculation errors when using the sine formula. This formula is quite long and involves squaring the differences of cross-multiplied components. You must ensure that your pairs are matched correctly. First, calculate L1, M2 minus L2, M1, then M1, N2 minus M2, N1, and lastly, N1, L2 minus N2, L1. One small slip in these pairings will throw off your entire result. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the formulas, it is very easy to make certain errors during an exam, so please pay close attention to these 3 points. Keep these points in mind as we move to our final summary. Key takeaways. First, remember that direction cosines, or DCs, are simply the cosines of the angles that a line makes with the positive x, y, and z coordinate axes. As we discussed in the second slide, these values are incredibly useful because they represent a unit vector. Second, let's review our primary tool, the cosine formula. To find the acute angle theta between two lines, you use the formula. Cosine theta equals the absolute value of L1 times L2 plus M1 times M2 plus N1 times N2. Just a reminder from our earlier slides, always use that absolute value to ensure you are calculating the acute angle. Third, we also looked at the sine formula. While it is a bit more complex, it is a powerful alternative. Sine theta equals the square root of the quantity L1 M2 minus L2 M1 squared plus the quantity M1 N2 minus M2 N1 squared plus the quantity N1 L2 minus N2 L1 squared. This is particularly helpful in more advanced vector calculus. Finally, the most important thing to remember is why we prefer using direction cosines over direction ratios. The use of DCs significantly simplifies our calculations because the magnitude of the direction vector is already equal to 1. This eliminates the need for that extra division step we often see with direction ratios. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before you move on to your practice problems. I hope this summary helps solidify your understanding. Great job today.